Hey guys, as we dive a little bit deeper into the study of fractals, we looked at how to generate fractals mathematically, so how to build them up from the ground up. And the first thing that we looked at were L systems. In this video, we're going to look at what are called iterated function systems, and the shorthand for that is IFS. Now, this is a huge field related to fractals, and we're going to try to look at some of the mathematical foundational elements of these types of systems and see how they build up our standard fractals. The idea of iterated function systems are that you take a shape, which you'd consider as your initiator, that very first piece of the fractal, and then we perform geometric transformations to that shape to build your generator. So your generator, if you remember back, we had the initiator, then the generator, and then you continue to iterate that generator over and over again on the resulting shape. So IFS, we're going to use functions to geometrically transform an initiator to create your generator, and then you're going to iterate that system. Very similar to L systems, there's two types of IFS, so of iterated function systems, deterministic and stochastic. So you have the deterministic side where everything is predetermined in the sense that if you ran the system again with the same set of initial conditions, you'd get the same resulting shape, the same fractal. Whereas there's a whole field called stochastic IFS where there's a randomness associated with the iteration of these functions. There's a probability associated at each step. So if you ran if you did it twice, you'll get different shapes, and that has its benefits in computer graphics and all sorts of different fields, but we're going to focus on deterministic. So I want to start with an illustrative example of what exactly iterated function systems are. So I've actually created my own fractal that I'm going to build up with an IFS, and I'm going to show you at each step what I'm doing. So what we're going to do is I'm going to start with a square, and this square is whatever the dimensions are, it's a square. Think of that as my initiator. So now what I'm going to do with this square is I'm going to make a copy of it, and I'm going to shrink that copy to 1/4 of the original size, and then I'm going to make a copy of itself and keep it the same size. So I'm going to get rid of this red box, and those are my pieces. So I have the original square, the copy of the square, and a copy of the square that I shrunk to 1/4 of it. Those are geometric transformations of the original shape. This is just keeping it the same, this is keeping it the same, and this is shrinking it. Fine. Well, now I'm going to arrange these. So I'm going to create, this is my generator that I'm going to create. I'm going to take the quarter, I'm going to put it in the bottom right hand corner of this one. I'm going to take the other copy and put it right up on the corner there. So this is a geometric transformation, again, of the original initiator. I've made two copies and I've arranged it in this way. But now, so that's what my system does. So imagine there's some functions that operate on this square and it makes this new shape that I've created. Well, now I need to do that again. So what you're going to do is take this shape, make a copy of it, then take this shape, make a copy, and shrink it to 1/4 of its size. So I'm going to get rid of this. So I've done that there. I've got the original shape right here, a copy of the original shape, and then a copy that's 1/4 of its own size. And now I'm going to arrange this the way that I had done before. So what we'll do is we'll take the original shape, leave it there, take the quartered copy, I'm going to put it in the bottom right hand corner of that shape, take the other copy and put it in the top left hand corner of that shape. So there's the second iterate of my fractal. All right. So again, those same functions, now the same functions we had from here to here worked to get from here to here by doing the same type of geometric transformation just on a new shape given by this. So let's do it again. Now I'm going to do it with this shape. So let's get rid of this. So now you can see I have the original shape, a copy of the shape, and then a copy of the shape shrunk to 1/4. And let's see how this will go. So keep the original shape where it is. Take the quarter up, so let's take this as the original shape. Take the quarter, put it in the corner, the bottom right hand corner. Take the other copy, put it in the top left hand corner like that. So there's my third iterate of this fractal that I'm generating. So again, you'd start here, you go there for 1 iterate, 2 iterates, 3 iterates, and you guys get the idea. I'd be creating this kind of cool looking geometric fractal with just a random rule that I came up with. Our job in this video is to learn how to define this function to get from the initiator to the generator with certain linear transformations, and I'll explain what that means, and that'll allow us to do those particular geometric transformations that we want to have happen. Now, in order to facilitate IFS in R squared, so we're going to focus only on 2 dimensions, we need to learn how to transform figures in R squared, in our 2-dimensional space, to other figures, other variants of that same figure. So here's kind of our goal. Suppose you start, so we're in R squared, so we're in our nice XY coordinate plane here, and suppose you start with a figure. Let's say it's just a square. Now we want to be able to do things to this square, and the things we want to be able to do are: 1, we want to be able to rotate the square in however much of an angle we want. 2, we want to be able to scale the square, so we either want to enlarge it or shrink it. And 3, we want to be able to translate that square, so we want to be able to move the square wherever we want it to go. So for example, with this square, we might want to transform it to another square that was over here in the plane and was maybe rotated a certain angle, so and reduced in size. So there we scaled it, we shrunk it, we rotated it, and we translated it. Those are the 3 things that we want to be able to do. Now it turns out that these 3 operations only require a very basic type of transformation called a linear transformation. And so now I'm going to define what linear transformations are, and we're going to look at how we can represent linear transformations on the space R squared. So a linear transformation is a special map from R squared to R squared that satisfies 2 properties. These 2 properties, you're probably familiar with these from either linear algebra or analysis or algebra. These are your linearity properties. So if you apply the map to the sum of 2 points, you could also put difference here, but we don't need it. So let's say you take 2 points in R squared, you sum them, and you apply the map. That's the same as applying the map to each one of those individually and then taking the sum. And also, if you take a point in R squared and you scale it by a vector alpha, that'd be the same as scaling the image of that point under the map F. These are your 2 linearity properties that we need to have a linear transformation. And again, the linear transformation is something that will allow us to rotate, to scale, and to translate any figure or any set of points in R squared. Now, linear transformations are really nice because we actually have a super easy representation for them that involves matrices. So if you have a linear transformation on R squared, you apply it to a point in R squared, which we can also represent as a vector. That'll be the same as applying a matrix, a constant matrix, to that vector, and then adding a translation vector EF. The matrix A here, these are constants, A, B, C, D. Those allow us to rotate and scale the vector XY, and then the translation vector EF allows us to move that point, the origin of that point, to wherever we want it to be. Again, you would apply this map F to every point within the figure that you're trying to transform. And one final note here, guys. Any transformation that can be defined in this way with the matrix and the translation vector is called an affine transformation, and I will be using this terminology in the next coming slides as we look at IFS in more detail. So I'd like to go through some basic examples that you might see in terms of basic linear transformations. And the first of those is just simply a rotation by an angle theta in the counterclockwise direction. So no translation and no scaling. Now, the way that this linear transformation would be represented would be with a translation vector of zeros, so you wouldn't be adding anything, and a matrix, a transformation matrix given by cosine theta minus sine theta and sine theta cosine theta. Okay. Some of you may have seen this before. That matrix there is called a rotation matrix. It's a rotation by an angle theta in the counterclockwise direction. So what that would look like in the plane is if you started with your original point here, you applied the transformation f to that original point, you would end up rotating through an angle theta and plopping your new point there. So if you applied, let's say your original point was the point 1, 0 on the axis, say it was right here, and you applied this map and you wanted theta to be 45 degrees, so pi over 4, then you would actually be applying the following map to your point 1, 0. So f of 1, 0 would be cosine of pi over 4, which is root 2 over 2. Sine of pi over 4 is minus root 2 over 2. And then you get root 2 over 2, root 2 over 2. And you can apply, you can do this matrix multiplication out, and you would end up with a point root 2 over 2, root 2 over 2, which would actually translate this original point to a point at 45 degrees at root 2 over 2, root 2 over 2. Now just a quick note here, we could actually apply the map to an entire figure. So let's say you had a square, and the square was right here, and it was all filled in. So this was a solid square, and you wanted to apply the map f to that entire solid square. Well, every point, so you could take the corners, and every point inside would be rotated by an angle of 45 degrees. So you'd be actually would be translating this entire square with all the points inside to a new location, and that new location would be rotated through 45 degrees, and the square would be now here. All right, so this is the type of thing we're going to be doing with IFS. If in addition to rotating by theta counterclockwise, we also want to scale by some positive factor r, so our r is going to be strictly bigger than 0. Well, in this case, we do the same thing as we did before with the rotation, but in addition to that, we have to put a scaling factor in front of each one of these terms. So we'll take that minus sign out of there. This, we put an r, and of course it's still minus, and then you have your scaling factor for each one of these. And then that would be your transformation to scale by r and rotate by theta. If r is bigger than 1, we get an expansion, so you'll actually get something that is larger, and if r is less than 1, of course still positive, it would be called a contraction in that case. The third example, what if you just wanted to scale by r? No rotation, no translation. Well, of course, no translation, you'd have zeros. To just scale by r, your rotation angle would really be 0. And so if you look back at our rotation matrix, you're going to get zeros here and zeros here. And you can just place your r's here, because ultimately when you multiply out with your matrix, you'll get rx and ry. So you've scaled the original vector xy by a scaling factor of r. If you just need to translate x by e and y by f, then you can do whatever you need to do in terms of the matrix here for your rotation and your scaling and potentially a reflection, and then you do your translation here. Another important transformation that can be done in this matrix form or this affine form is involves reflections, either about the y-axis or about the x-axis. If you want to reflect about the y-axis, that would be essentially folding across the y-axis. You just need to have the relative signs in your matrix like this, so that you're essentially changing the sign of x and keeping the same sign of y. And what it does is it folds it, so your line in this instance would be reflected across the x-axis, across the y-axis, and then for the x-axis, very similar. You're going to be folding about the x-axis, and if you change the sign of y and not the sign of x, you will get a mirror image across the x-axis. All right, and this is very helpful when we're transforming geometric shapes as well. Now that we have an idea of what these affine transformations look like, we can talk about the next important factor of IFS, and that is contraction mappings. So a map from r squared to r squared is called a contraction mapping if there is some factor, we call it the contraction factor, that lives between 0 and 1, such that when you apply the map to 2 points in r squared, the distance between those 2 points after the map is applied is less than the distance that it started with, that they started apart from one another, by the contraction factor alpha. These double bars are what we call Euclidean distance in r squared, and it's just the length of the hypotenuse between those 2 points in r squared. All right, so you can think of this as a contraction mapping is a map where the scaling factor, the r we were using on the previous slides, is less than 1, and of course bigger than 0. This now leads us to the definition of an iterated function system. Now, this system, the idea is the same, but you'll see different definitions in different textbooks, just like with the concept of chaos. But nonetheless, here's the general idea of it. Suppose you have some region S in r squared. So we're only going to focus on r squared. And this region S is closed and bounded, so you can think of that as your initiator. And then you have a collection of n contraction mappings on r squared, and we defined contraction mappings on the last slide. If you take the collection of those contraction mappings together with your region S, this is what's called the iterated function system. And what we do with our contraction mappings is we actually take a union of those mappings, and we call this the Hutchinson operator. Now, the Hutchinson operator is what's going to allow us to create our fractal. And what we do with that Hutchinson operator is we start to iterate the region S. So you'll find f of s, f of s, etc. That's where the iteration part comes in. Now, if you look at the limit of this, so if you look at the limit of the iterates, so this would be f to the n, that would be the nth iterate, or the nth composition, as n goes to infinity, it'll converge to what we call a sub f. And this is the attractor of your iterated function system. And this attractor is exactly the fractal. One quick final note, guys, before we dive into some examples. This n, for the number of iterates of our composition, is much different from these original indices of your original contraction mappings. So once you create your contraction mappings, you create your Hutchinson operator, and then you iterate the entire union. So you iterate the entire Hutchinson operator over and over again. So just be aware of that. So let's do our first example with the Sierpinski triangle, or the Sierpinski gasket. And our job is going to be to actually find an iterated function system that allows us to create this fractal. Of course, this is only the first and second iterates. This will go all the way to that gasket. So let's see how we would do this. The first step, this is the initiator on the first step. We're going to actually put this into a XY plane. So imagine this is your x-axis, this is your y-axis. Okay, and that'll be the same for all of these. We need to know where we're keeping our origin. So my origin will be the same for all of these triangles in each iterative step. Okay, so from my initiator, notice what's going to happen here. I need to take this original triangle and I need to make 3 copies of it. 1 blue, 1 red, and 1 green. Okay, so these are actually 3 different operations. I'm going to take this triangle and I'm going to geometrically transform it to become that blue triangle. I'm going to call that the F1 transformation. Then I'm going to do the same thing with the triangle. I'm going to make this red triangle. I'll call that F2. And then I do the same thing and I make the green triangle. And we'll call that operation F3. So ultimately, you're doing 3 operations at once. F1, F2, F3 to create 3 copies of the same triangle and move them to particular places. So there's going to be scalings involved and there's going to be translations involved. And we need to figure out exactly what those affine transformations are for F1, F2, and F3. So we're going to find these affine transformations. I'm going to start with F2 since that's actually the easiest. So look at that red transformation. What we're doing is we're shrinking every dimension. We're shrinking the x and y coordinates of the original triangle by 1/2. And we're not actually translating it anywhere. So we're simply scaling the x and y coordinates of the original triangle by 1/2. So there's F2. There's no translation. Then if we move to F3, again, we scale that original triangle by 1/2. So that's going to shrink it down. But then we do need to move the original triangle over by 1/2 for the x coordinate. So this will be 1/2 and 0. The reason I know it's 1/2 shift, and I should have written this before, these original dimensions, this is 1 originally with a height of it's equilateral. So all of these dimensions are 1, 1, 1. Okay. Now F1, the blue one, is a little bit harder. So again, we scale the whole triangle by 1/2. But then we need to know where we're translating the blue triangle to. The easiest way to see this is to actually just look at where the new origin is for that blue triangle. So there's the new origin. I need to find the points, the x coordinate and the y coordinate of that new origin. And the way that you can go about doing this is just with geometric arguments. So you need to kind of make some triangles. These are all equilateral triangles. It's very geometric. You need to move the x over 1/4, since this point here, this is 1/2. This point here is clearly half of that, so it's 1/4. And you need to move the y value up √3/4. And again, you can use just a small geometric argument for that, which I'm not going to go into very much here. So I have now 3 transformations that I will do to the original triangle to make that second step to make the generator. And understand that we have to add these transformations together or take a union of them in order to do all 3 of them simultaneously. So our Hutchinson operator, when we talk about the Hutchinson operator, F is F1 union F2 union F3. The collection of these mappings, F1, F2, and F3, together with the original triangle, which we'll call S, that's this original triangle here is S, is this whole thing here is our actual IFS. So when you're creating the IFS, you can describe the region and the three functions. The Hutchinson operator is the one that we will iterate. So I'm going to take the limit of iterates of this as applied to the original triangle S. And what that's going to equal is the following. It'll equal your Sierpinski gasket, or your final Sierpinski triangle fractal, which we're going to call the attractor of this IFS system. Okay. Now for shorthand, because we use these affine transformations so much, oftentimes it's helpful for us to actually make a little table of the values A, B, C, D, E, and F for your 3 functions, F1, F2, and F3, to describe the IFS. And the ABCD comes from the affine transformation form, ABCD times x, the vector xy plus EF. And so all I've done here is filled in the constants from those 3 contraction mappings that we have above. So the IFS is the collection of all of these contraction mappings along with the original triangle S. The limit of those is the attractor, which is your Sierpinski gasket. And these are the constants that I would program into a computer in order to accomplish this fractal, to create that fractal. All right, let's do the same thing for our other favorite fractal, the Koch curve. We're going to find the IFS for generating this fractal. So the Koch curve starts with your initiator, which is a line. We are going to put this into R squared. So this is your y-axis, and this would be your x-axis. Same thing here, the y-axis and the x-axis. The reason that that's important is because we actually we're essentially defining what the origin is in both images. Okay, so the original initiator has a length of 1, so keep that in mind. Each of these has a length of 1/3, so each of these segments is scaled down by 1/3, and they're all copies. So these are all copies of the original line segment. So there's actually 4 things happening. The first thing, you're going to take the line and you're going to make a copy of it and place it here. So that's what we'll call F1. That's the first geometric transformation. Then you're going to take the line, you're going to scale it down by 1/3, you're going to move it and rotate it. So that's F2. So there's a few other things happening. Notice what has to happen to get this line from 0 to 1 over to start at 1/3 and go up this way. There's a few geometric transformation. There's a few steps in terms of translating, scaling, and rotating. So then we'll do F3 is this other line here. We have to be able to get that there. And finally, I'll use my last color of F4. So we're going to define these as affine transformations to see what happens with each one. So we'll start with F1. That's nice and easy. You're going to take the original line segment from 0 to 1 here, and you're just going to scale the x coordinate by 1/3. And since the y coordinate is 0, it doesn't matter if we scale the y coordinate by 1/3 either. So what we're going to do for F1 is scale both the x and the y by 1/3. The reason I'm doing that is because in the next steps, you might have y values that are not 0, so scaling the y by 1/3 is really important as well. So there's F1. Let's skip on down to F4. F4, we do have to scale the original line segment down by 1/3, and then we need to push the start of that line segment out to a point, an x value point of 2/3. So we're going to be pushing that, translating that x coordinate out by 2/3 for the start of that line segment. Now back to F2. A couple things have to happen. We have to scale it by 1/3. So we're going to scale by 1/3. We're going to rotate the line by 60 degrees, since that's an equilateral triangle. And then we're going to translate the x coordinate to get it to start right here, which is 1/3. All right, so we have to do these three things, and we're going to use what we learned previous in the video. It's going to look as follows. So it'll be 1/3 cosine 60 minus 1/3 sine 60, and then we'll have sine 60 with a 1/3, of course, and 1/3 cosine 60. That's going to be xy, and then, of course, plus the translation, which is 1/3 and 0. Now, of course, I can compute the cosine and the sine, so I'm going to do that here. F3 is very similar to F2. I do need a little bit more room with where I'm working, so I'm going to zoom down over here, and we'll see what we can do for that. So notice we are going to have to scale by 1/3 for F3, and then, so when you scale by 1/3, so think about it in this way. We would first scale by 1/3, so we get our line segment, which would be here. Then I want to rotate, so I would rotate it so that it's actually down in the other direction by 60 degrees. So we're going to go clockwise 60 degrees. And then you need to translate that so that the start, the origin, now comes up over here. So we have to think about how far that origin is moving on our original picture. And you'll notice that the x coordinate is definitely 1/2, and the y coordinate up here, so this will be 1/2, and the y coordinate of that point is √3/6. Again, that's a geometric argument to figure out the height of this point to translate that origin. So we have to do these three steps. Now the rotation, remember our rotation is always in the counterclockwise direction, so if I do want to rotate down 60 degrees or clockwise 60 degrees, I'm going to rotate minus 60 degrees. And then I want to translate both my x and my y points. So I'm going to go 1/2 √3/6. Okay, so you can put this in. So we have our green f of xy, and we would do this as a matrix, an affine transformation. So putting all of that information into our standard affine transformation, you get what you have there, and then we can simplify these trigonometric functions. And these would be your 4 contraction mappings. So that of course is F3. Now our IFS, remember, is the collection of these 4 contraction mappings. So this would be the collection of F1, F2, F3, and F4, along with the region S, which in our case, the region S would just be the line, our original initiator line. Okay. Now the Hutchinson operator is going to be the union of all of these. So F1, union F2, union F3, union F4, because you need to perform all 4 operations and put them together. So take a union. The limit, if you continue to iterate this Hutchinson operator an infinite number of times, is going to be the attractor of the Koch curve, which is the following. It's our standard Koch curve that we are familiar with. So this function, this system would be what we would program into the computer to achieve this Koch curve. And I'm going to just draw out the table in a moment of all of the affine coefficients that we would use. So you can see here on the right, I've combined all of the constants from the affine transformations of F1, 2, 3, and 4 to create my IFS that would allow me to take my initiator and continue to create our generator with the IFS, and then take a limit to get my Koch curve fractal ultimately. One of the most famous IFS created fractals is what we call the Barnsley-Fern, and you guys actually were exposed to this in one of your RWRs recently. One of the coolest things about IFS is that you can do a quick Google search for any fractal that you like and just look for the code of Barnsley-Fern or the code of whatever fractal it is, and you'll be able to find those affine transformation constants that would allow us to create the Fern with computer aids. All right, so these are constants that would allow us for our, they're using W here, but 1, 2, 3, 4, allowing us to create this with an IFS transformation. So in the few examples we just did, you'll notice that they're all affine and linear transformations. The big question is, do we need this in IFS? The answer is no. So this is literally just the tip of the iceberg, guys, for iterated function systems. The contraction mappings that you use in an IFS can actually be much more complicated. They can be projective transformations, they can be Mobius transformations. There's a whole world out there for creating these IFS type fractals. So for your daily question today, what I want you to do is find a fractal that is created with IFS using affine transformations, and I want you to just upload to Husky CT, upload a little screenshot of your favorite fractal that you found, along with the code, so the affine transformation constants, if you can find them, for how to create that with the A, B, C, D, E, and F. All right, guys, so that wraps up our introduction to IFS. You will have some homework problems on this where you're going to try to find an IFS, so to try to find that system to create a given generator and thus create a given fractal. So please practice that. The exciting part is that there's really just so much more to this subject. We just don't have time for it. You can look into computer programming involving IFS systems. You can look into so many things regarding this topic, and there's a lot more in the complex world as well. So ultimately, it would be great to have a second semester of this course, but we did as much as we could, and I'm excited to wrap it up with your projects for the year. So I will talk to you guys soon, and don't forget the daily question.